All right, today we're going to peek behind the curtain. You might even call it an Iron Curtain 2.0. We're talking about this incredibly complex web of air defense systems. But look, this isn't about politics. Nope. This is all about the pure engineering challenge. I mean, how do you even begin to build a shield that can see everything and react in a split second? Well, that's what we're here to do. We're going to break down the guts of this thing. The advanced radar, the super fast signal processing, all the tech that makes it tick. So let's dive right in.
So let's start with the big question, the one that probably keeps a lot of engineers awake at night. Seriously, how do you design a system to defend against, well, everything? We're talking threats from all directions, at all different speeds, different altitudes, and they're all coming at you at the same time. It's not enough to have a smart solution, it has to be unbelievably fast and perfectly in sync. It's a massive puzzle that really stretches what's even possible in a bunch of different engineering fields.
Okay, so here's the game plan for today. First up, we'll get a real sense of the challenge we're dealing with. Then we'll get into the super clever, layered solution they came up with. After that, we'll meet the hardware itself, the systems doing the heavy lifting. Then we'll geek out on the tech backbone, and finally, we'll see how it all comes together as one big, integrated defense network.
Right, so before we can really appreciate just how elegant the solution is, you gotta understand how incredibly complex the problem is. I mean, we're talking about a combination of some seriously advanced tech. Things like radar, radio frequency systems, RF, and signal processing that has to work faster than you can blink. Yeah, just try to picture this for a second. You've got threats coming in high and screaming fast. At the same time, you have others flying low and slow. And everything in between. The system has to handle all of it, all at once. This isn't just some tough engineering homework assignment. It's the whole reason this kind of tech was even invented in the first place. So, faced with a problem that has so many moving parts, what do? Well, the engineers came up with a really brilliant strategy. It's called layered defense. The big idea is, instead of trying to find one single magic bullet that does everything, you build a shield with multiple layers, and you give each layer its own special job. And the idea behind it is actually pretty simple, but super powerful. It's like this. Don't build a jack-of-all-trades, master of none. Instead, you create a whole team of specialists. Each layer of this shield is a unique piece of hardware, and it's engineered to be an absolute expert in its own area, whether that's scanning the very edge of space or playing bodyguard for a single important spot on the ground. So you can basically break it down into 3 tiers. You've got your outer layer, which handles the long-range, high-altitude stuff. That's your first line of defense. Then there's a middle layer for more general area defense. And finally, you have this inner layer that acts like a last resort, close-in bodyguard. The coolest part? Each layer is built to pass threats off to the next one without missing a beat, creating this incredibly tough defensive web.
Okay, so now let's actually meet the hardware. Let's look at the specific systems that bring this whole layered idea to life. These are the tools that make up each of those tiers we just talked about.
So here they are, the 3 main players in this defensive lineup. You've got the S500, that's for the far-out, high-altitude layer. Then there's the S400, which is kind of the long-range workhorse of the group. And finally, the Pantsir, for that up-close point defense job. And as we're about to see, the tech inside each one is custom-built for its role. Starting at the very top, the outer ring, you have the S500 Prométhée. Think of this as the big outer shield. It's designed to go after the toughest targets out there. We're talking things moving at insane hypersonic speeds, way up at the edge of the atmosphere. To pull that off, it needs unbelievably powerful radar and some seriously smart, predictive tracking that can figure out where a target is going in just microseconds. That is a huge engineering lift, right at the limit of what computers can even do. Next up is the S400 Triumph. You've probably heard of this one. It's the most famous of the bunch. It really is the workhorse, designed to defend a pretty big chunk of airspace. Its real engineering magic trick is its ability to multitask. It uses its powerful radar and some clever signal processing to track dozens of different targets all at the same time. It's like juggling, but with missiles.
And rounding out the team, we have the Pantsir. This is the bodyguard, the absolute last line of defense. Its entire purpose is to protect the bigger systems, like the S400, from anything that manages to slip through. So it's engineered for one thing, pure raw speed. It uses both radar and electro-optical sensors to find and lock onto anything close by in an instant.
Okay, so we've got these different systems, right? Each one's a specialist in its own right. But
how do they actually work together? What's the secret sauce, the common tech that turns them from a bunch of individual units into one cohesive, intelligent network?
Well, the answer is in what we call the technology backbone. This is the stuff under the hood, the core tech that all these systems share. It's what handles all the heavy lifting, the sensing, the processing, and the communicating.
Right at the very heart of this whole thing is radar. It's literally the eyes of the entire network. Now, modern systems use something called a phased array, and it's really cool. Instead of a big, clunky dish that has to physically turn around, a phased array is a flat panel that can steer its radar beam with just electricity, no moving parts. Imagine thousands of tiny antennas all working together, pointing a beam of energy anywhere they want in the sky instantly. That is the key to how these systems can track so many different things at once so incredibly fast. But here's the thing, a raw radar signal is, well, it's mostly just noise. It's a mess. And that's where signal processing comes in and becomes absolutely critical. First, the system has to cut through all the background noise and clutter. Then it has to actually find and identify something that might be a target. And then it has to calculate where that target is headed. And all of this, it happens in a tiny fraction of a second. It's what turns a chaotic mess of data into a crystal clear picture of what's happening. And what ties all this together? You can think of it as the network's nervous system. You've got the RF systems, which are like the vocal cords, managing how all the signals get sent and received. Then you have the super fast communication systems, making sure all the different pieces can talk to each other with practically zero delay. You can even bring in UAVs and drones to be extra eyes in the sky, just feeding more and more data into the network. Now, of course, it's one thing to design a system like this on a whiteboard. It's a whole other challenge to make it actually work reliably out in the real world. And that means solving some massive engineering hurdles. You can boil it down to 4 huge challenges. First, all that processing has to happen in real time. We're talking fractions of a second. Second, the signals have to cut through all kinds of electronic noise and interference. Third, you have to get all the pieces, the radars, the launchers, the command posts, to work together perfectly. And maybe most importantly, the whole thing has to be ridiculously reliable. It has to work flawlessly when it matters most. All right, so let's pull all of this together. When you take that layered strategy, add in those specialized systems, and power it all with that amazing technology backbone, you end up with way more than just a pile of missile launchers. You get something else entirely. And if there's one thing to take away from all this, it's this. The real power isn't in any single missile or any one radar dish. It's in the network. It's how everything is so deeply integrated. The sensing, the communication, the computation. That's what turns a bunch of separate pieces of hardware into what is essentially a single, intelligent defensive organism. And that really brings us to the final question, doesn't it? We've just walked through how breakthroughs in radar, RF engineering, and signal processing built the complex systems we see today. So it really makes you think, what's next? What new engineering leaps will define the next generation of defense? What would an Iron Curtain 3.0 even look like?